Had our first assessment this morning, which we call reading assessment. We're wearing a uniform in the course. And that sports this huge lambda in the front. And you may have seen this lambda in many places in computer science. It even appears as a keyword in your favorite programming language, Python. So some of you may wonder, what is this lambda all about? So today you get a little bit of an idea. We're going to dig deep into the history of computing to find out what this is, the lambda-calculus. And I'm going to connect that historical perspective with today's needs for Computer Science 101 teaching. So we're going to bridge from the early days, even before computers, computing before computers, what was that? All the way to today's need for teaching as I see it. So I'm going to talk about a notional machine for modern scripting languages. That means a way to think about what happens when programs run based on this ancient lambda calculus. So what are we talking about when I say modern scripting languages? Python, JavaScript, Lua, these are all instances of languages that have a lot in common. So they are lexically scoped languages. I will be talking about that in a minute. First-class functions, functions as first-class values. That's where the lambda calculus comes in. Variable assignments, stateful data structures, automatic memory management, dynamic typing, and a statement-oriented syntax. So these languages have all of that in common. And my challenge when I teach computer science is to give students who don't have any prior background, first year computer science students, an idea what happens when programs run. What happens when programs run? That's the challenge. And I think this is often glossed over, so we're sort of assuming that we get some intuition of here's a program, you know, you press a button, it runs. You get an idea by running enough programs. You get an idea what happens when the program runs. So I would like to improve over that and come up with a framework that allows students to systematically discover what happens when programs run. So that is called a notional machine. So basically a mental model of program execution that can be taught to, let's say, a high school student or even a primary school student with enough patience. Step-by-step execution of these programs of this language family without reference to compilation. So we would like to explain the execution of programs from first principles without saying, oh, we're going to first translate this program into something, and then you need to explain what that something does to your program. No, we want to do it from first principles. Now, the approach is to start with a given program and decompose the program systematically, step by step, until we have basically some sort of atomic units that we can explain very easily. And that's sort of the overall approach. So our example language will be JavaScript. If I have enough time, I can give you a little demo later. Python and Lua would work in a similar way. My background is I joined NUS a year before the School of Computing was formed, so I'm sort of a dinosaur here. And you can look up when that happened. I'm teaching programming language and programming language related courses here at the School of Computing. And currently I teach CS 1101S, yep, that's this one, in a team that also includes Aloysius here, as well as my academic colleagues Boyd Anderson and Samka Rasnayaka. I'm also academic advisor of the Source Academy, you mentioned. It's a learning management system built by NUS computer science students, designed for this sort of thing, computational thinking, and specifically designed for first-year computer science courses. The agenda, I'm going to start with the origins and a bit of theory of this lambda calculus thing. The birth of the lambda calculus, core concept and notation. I'll cover beta reduction and its pitfalls, including how early computer science pioneers misunderstood the lambda-calculus, and as a result, basically introduced a major design flaw that took years and years to fix. Then I'm going to look a bit at the programming reality, what this means for today's programming languages. I'll have a slide on evaluation strategies, lazy versus eager evaluation, also motivated by this lambda calculus, and I'll cover how this notion of lambda influenced today's programming languages. And then I get into this notional machine. So I'm going to take you through a journey where we start with a landmark paper in computer science, the Landin's SECD machine, and simplify it step by step to get to the notional machine that we use in our course CS111S. So from SECD to the CSE machine, which incidentally I would like to stand for Computer Science Education, CSE. And a bit of an outlook of what we're doing. So the first part, beginning with lambda. Alonzo Church was actually a mathematician at Princeton who was thinking about a foundation for mathematics. So back in those days, people were thinking, can we have a solid foundation that underlies all branches of mathematics? And one approach in that effort was to think about computability. So it would be great to have a foundation in which everything is computable. So they were looking for a mathematical framework that allows you to characterize what functions are computable. And Alonzo Church came up with this extremely minimalistic framework that allowed him to compute, as it turned out, any function he could think of. And he proposed that as a foundation for that sort of effort in mathematics. So the goal was to create a formal system for expressing computation, and this preceded the Turing machine. Many of you may know the Turing machine from your theory courses, which is also a mathematical framework to describe computation, but it's very much mechanistic in the sense that it could serve as a basis for real computing machinery. So it had the idea of, okay, now you take the next step. So it had the underlying intuition of a processor, whereas Church's lambda calculus had a simple mathematical framework that underlies computation. Fun fact, Alan Turing was Church's PhD student. So they together came up with the Church-Turing thesis, which states that the lambda calculus and this Turing machine framework are equally expressive. In fact, you can show that pretty much all computational frameworks that you could come up with, all deterministic sequential mechanisms for doing computation, are equally expressive as long as they have some basic ingredients. So that was a bit of a surprise. All these computing mechanisms are equivalent. And that includes this lambda calculus, and people today explore this and see how simple can we make mechanisms to still express all computable functions. And people come up with these weird results that things like the game of life are so-called Turing complete. So it seems like this notion of universal computation is very easily achievable. And as long as you have some basic computational mechanisms in place, boom, you can compute all possible functions. So that was the background there. And why do we want that that utmost simplicity? Well, in mathematics, you want to have things as simple as possible so that you can prove things. Your proofs should cover your whole language, and the smaller the language is, the easier your proofs are, the smaller your proofs are. And that means the lambda calculus was then used as a formal semantics for computation for programming languages. It's also the basis for type theory and proof systems, and the inspiration for a family of programming languages called the functional programming languages. ML, or standard ML, Haskell, Scheme, and many other languages you may be familiar with. OCaml, I learned that the company Jane Street is a sponsor of this series of events. Jane Street is famous for using OCaml as their programming language, so which is, of course, a functional programming language. For you as a programmer, the lambda calculus is the underlying theory, the underlying or origin of what you know as higher order functions. Functions that you can pass as arguments, that you return from functions. That is basically directly coming from the lambda calculus. And if you look at programming language implementation or look at programming language semantics, the notions of closures and scope are directly motivated by the lambda calculus. And many functional programming patterns have their origin with these very early ideas. The basics. Here is the lambda calculus. So you have variables. You have functions that you can define. You write functions like this. Lambda x dot m means we define a function with a parameter x, and the body of the function is m, which is an expression. And how do these expressions look like? Well, they can be variables, there can be these lambda expressions, and there can be applications. And that's it. You apply some expression to some other expression, and you have a new expression. So these three things are all there is in this lambda calculus. You will agree with me that a minimalist programming language. No loops, no recursion, no declaration apart from this way to introduce a function that has a parameter x and that has an expression as its body. And everything is built from these, and you can actually do computation with this. Here's an example. This is the identity function, a function that returns its argument, lambda x dot x. Here is a way to apply this identity function to the variable y, right? You apply this function to y, and the result is, of course, y itself, right? So the function returns its argument, and therefore we return y. Examples, if you add a bit of support, at least to come up with examples, you would have, you would add additions and numbers. As it turns out, numbers can be represented in this lambda calculus itself. You don't need to add them to the language. So you don't need to build in these numbers. You can come up with lambda expressions that represent individual numbers, and you can do addition and subtraction, multiplication, all these arithmetic operations. Lambda x, to repeat, means the function of x, and x plus 1 is the function body when we say lambda x, x plus 1. So this is a function that takes x as argument and returns x plus 1. And in JavaScript, this would look like this: function x, return x plus 1. Or indeed, in a shorter notation, x arrow x plus 1. You see here, this syntax in JavaScript looks very similar to this lambda-calculus directly. And in Python, it looks very similar. You have lambda, even the keyword lambda, x colon x plus 1. So directly coming from this ancient root, the 1930s, prior to computers. This guy invented a mechanism to execute these programs, to write programs. So there wasn't that notion of writing programs, but as a fundamental mechanism to describe computation. 2 argument functions. Well, you pass the argument one after the other, right? So lambda x, lambda y. X plus y is a function that takes x as argument and returns a function that takes y as argument, and that function returns x plus y. This is called currying, and when you apply then such a function like this, lambda x, lambda y, x plus y, applied to 3, gives you a function that takes y as argument and returns x plus y, where x is 3. And that you apply to 4, and that means you get x plus y, where x is 3, and y, where x is 3 and y is 4. And that means the result is 7. Here's a weird program. This is the simplest infinite loop you can write in the lambda calculus. Why this is an infinite loop? Can anyone see this? Well, the result of applying this function to this argument is going to be what? We're replacing x in the body here by lambda x, xx, right? Xx is the application of x to x. Okay? So what's going to happen is that we are replacing this x by this and this x by this. We end up getting the whole expression back, right? We're going to end up lambda x dot x as a result of replacing this x, and lambda x dot x as a result of applying this x. So we get the identical function back, and that means we have an infinite loop. So that gives you a little bit of a feeling for the expressive power here. There are relatively simple expressions that do things like recursion. You've probably heard of the investment company, the Y Combinator, right? The origin of the name Y Combinator is actually an expression, a lambda expression, that expresses recursion. So they took this name from computing theory and used it a bit as an inside joke to refer to their investment company, which of course deals a lot with IT-related companies. Okay, the core of this whole mechanism is what is called beta reduction. So you have a rule that says what happens when a function gets applied. You've seen that already, right? We've seen that we want to replace the parameter in the body by the argument. This is a function application. That is expressed like this. The result of this beta reduction, the result of the function application, is the body of the function, where we replace the parameter x by the argument n. And n and m can be any expression. So more formally, we replace all 3 occurrences of x in m with n. And again, here's an example. So we use this as an instance of this rule. That means this m becomes x plus 1, n becomes 5, and the result is the body of the function x plus 1, where we replace x by 5. This is a replacement. So wherever x is, sorry, I think I made a mistake here. So this should be x plus 1, where x is replaced by 5, and the result of that is then 5 plus 1, and the result of that is 6. All right. The pioneers of programming languages discovered this lambda-calculus, and one branch back in MIT was to use that as a foundation for the what they wanted to call high-level programming languages. So back then there was pretty much only machine code, assembler maybe, and they wanted to have very expressive languages. They came up with versions of this lambda-calculus and added things like defining functions. So giving a name to a function, this can also be done in the lambda-calculus. But they added specific expressions in the language for defining named functions. But amazingly, they didn't understand the lambda-calculus well enough to avoid a major mistake. So the lambda-calculus specifies that the names that appear in the body of the function only refer to the closest surrounding declaration. Right? And just an idea here, how many of you have taken CS111S? Okay, how many have not? Oh, okay. So there are certain probably things that are imprinted in your memory, no matter how long you have taken, how long ago you have taken CS111S. So you remember this phrase, the closest surrounding declaration? Yeah, that comes from the lambda-calculus. So, but the pioneers of this Lisp family of languages didn't actually fully understand what it means for a name to refer to a declaration. So they built in what is called dynamic scoping. So the expectation when you run this program, G applied to 5, is, okay, so you're applying F to 3, and here you actually have an occurrence of Y that doesn't have a declaration surrounding it. So this should be a programming error. But the pioneers of Lisp got the binding mechanisms wrong. So when you have this situation, when you're executing a function application G applied to 5, this binding of Y to 5 survives this function call, and that means in this expression, x plus y, basically 3 plus y, this y refers dynamically to the previous binding. So the bottom line is variables need to refer to their declaration, not to the current binding. So this was fixed in the future languages of Lisp, Common Lisp and Scheme, that introduced this notion of lexical scoping, which is, of course, the correct way of doing things. And all programming languages today basically follow this mechanism of lexical scoping. So when you look at a program in any language that you know, you look at a name of an occurrence of a variable, you can actually figure out directly what declaration this name refers to. It's an obvious idea. And that goes all the way back to the lambda-calculus. All right, so that's just give you a little bit of an idea what's how this a flavor for this lambda-calculus. Now let's look at more today's programming practices. What was an area of interest for these early pioneers, the mathematicians looking at computability, was, now you have a given expression in this lambda-calculus. Is the evaluation going to terminate? You saw this very simple loop, right? Are there strategies to evaluate in a given expression so that you get a value at the end. You get an expression that cannot be further evaluated. And they found out that there is indeed such a strategy. So if there exists a so-called normal form, a particular strategy of going and making progress in your computation, finding these applications that can be reduced, finding these beta redexes. There's a strategy to find these beta redexes so that you will get a normal form, you will get a program that cannot be further simplified if it exists. You've seen this infinite loop. For this infinite loop, no normal form exists. It's an infinite execution regardless of how you choose to apply these, how to execute these applications. But there is a strategy that if such a normal form exists, the strategy will find it. And that strategy is called normal order reduction. The normal in normal order reduction means it will find a normal form. It will find the form that cannot be further simplified if it exists. So that motivated some pioneers in functional programming to use that evaluation strategy as the underlying strategy for running programs. And the most famous programming language that uses a variant of this normal order reduction is the language Haskell. It's a variant of normal order reduction because it includes a particular optimization called lazy evaluation. However, what we have in most programming languages doesn't have this nice theoretical property, but it is a bit easier to handle, a bit easier to reason about. That's called applicative order reduction. So that is what you expect in programming languages. When you have a function application, you need to evaluate the arguments of the function application before you do the application. So that eager execution of or evaluation of the arguments is the core ingredient of applicative order reduction. And a simple example to demonstrate the difference, you have a function that takes x as argument and returns x plus x. Now you apply that function to to 3 plus 4. Of course, you want to compute 3 plus 4 before you do the application. And that means the next step, you reduce 3 plus 4 to 7, and then you apply the function, and that gives you x plus x, well, 7 plus 7, because you replace x by 7. You replace the parameter by the argument. That gives you 7 plus 7, and gives you 14. Normal order reduction in its simplest form will actually do 2 additions in this evaluation. So you are taking the entire argument expression and replace it and substitute the parameter by that expression. That gives you 3 plus 4 plus 3 plus 4. It's actually a longer computation. But this strategy guarantees that you find a normal form if it exists. Of course, lazy evaluation then can optimize this and make sure that you only do one addition. In modern programming languages, we have that lambda-calculus built in. So actually, the lambda-calculus, as Alonzo Church invented it, is a direct sub-language of Python. So you can directly translate every lambda-calculus program into Python and run it. And what you will get is a normal form using applicative order reduction, or using applicative order reduction, a particular strategy. Same for JavaScript. So you have these lambda expression in JavaScript, and the reduction follows pretty much directly the lambda calculus invented in 1930. I want to spend a bit of time, probably have 10 minutes or so left, on a more realistic framework to run these programs. What is the problem with this beta reduction? What is the problem with this particular framework of replacing expressions by other expressions? Now, first of all, this pure lambda calculus becomes unwieldy. There are ways to introduce recursion using these Y combinators, but it's for more realistic programs, it's very hard to find where the computation will happen in this applicative order reduction. It's hard to find the place where to reduce next, even if you have fixed a particular strategy. Recursion can be done, but it's really weird. And another question is, can we do state? Can we do assignment? And that's a bit difficult in this pure framework. So instead, we would like an execution machine, a mental model that allows us to run programs in this language and more interesting languages that that are compositional and that allow us as humans to properly understand what's happening. And the underlying mechanisms for the lambda calculus, the underlying framework was laid by Peter Landin in 1966 in a landmark paper called The Mechanical Evaluation of Computer Programs, of lambda expressions. And he called this framework the SECD machine. SECD stands for the component of the computational framework. So he introduced what he called an operand stack, an environment, control, and dump. So SECD. It's compositional. That means it doesn't involve a compiler. A given program is decomposed into its parts on the fly, and these parts get handled one by one. So we break down a big expression into its component expressions until we have primitive expressions, and there are rules for handling those primitive expressions. It can handle state, although Landin didn't elaborate on that. I'm not sure if he knew when he described the SECD machine, but it can handle state very easily, and it can serve as a realistic implementation method. That was the intention, and people then built actual implementations of functional programming languages based on this SECD machine. That was the first reference implementation, the first realistic reference implementation of the lambda calculus. How does it work? Here's the SECD machine in detail. We start with the given expression as the third component of a state, where all the other components are empty. So you start with an empty operand stack, an empty environment. You start with a given expression, E, and an empty dump. And if you're doing your computation, you keep simplifying this expression. You decompose the expression into its parts. And eventually you might actually, what you have here as C, as control, is a sequence of expressions that still need to be evaluated. The control says, these are the things that you still need to handle. And this colon means, okay, you have on top of your control stack, this is a stack, is a variable. And you have a whole bunch of other things that you still need to do. What you do with a variable, you look up the variable in an environment. That's where this E comes in. So we are looking up this X in E. An environment will know the binding of X, and that result you push on an operand stack S. So you end up with a state, again, 4 components, in which your operand stack has one more element,
which is the result of looking up this variable x in the environment E. Your environment stays the same. Your control now doesn't have x anymore, so that means you have the remaining things that you still need to do, and a dump D. I'll talk about the dump in a second. You have, if your control is a lambda expression, what do? Well, you need to be ready to execute this lambda expression. So you form what is called a closure that includes the current environment. So the current environment is stored in this data structure that you push on this operand stack. Then the application. So if on top of your control is an application, lambda-calculus, yeah, m applied to n, we decompose it. We say, okay, first you deal with m, then you deal with n, and then you remember to do an application. What does an application do? So if your control has this application instruction, this is an instruction actually, this is a component that appears on the fly, that gets generated on the fly. So if your control has this application instruction, what do we need to do? Well, we expect the function to be applied and the argument to apply it to on our operand stack. And what we do, we assume that the function that we're applying is such a closure, and then we simply need to remember to execute the body of the function. Well, remember, this was the body of the function that we stored in this closure, m. So we need to push that, push that body of the function on our control. Our control now consists of the body of the function. What operand stack are we going to use? So now the next thing is we need to execute the function, right? The operand stack to use is empty. What happens when we return from the function? Well, we need to do a bit of bookkeeping. We need to remember the current operand stack, the current environment, and the current control in a data structure that we remember in order to return from the function. This is sort of a runtime stack in this SECD machine. So you see here, you get a feeling that's quite a mouthful to explain to a first semester student, right? So that's where we try to innovate a bit. We try to make this as simple as possible, and that comes from an. So this is the motivation. It's too complex for teaching. 4 registers to track. The complex dump management, and it's hard to visualize for students. Can we simplify this? Yes. So we can make the stack global. We can make the control global. And once we have done that, there's no need for a dump anymore. So that's the idea. So here is how to make the operand stack global. So instead of coming up with an empty operand stack when the function gets applied, we just keep that operand stack. We keep the operand stack the same. And when we return from a function, we just put the return value on the operand stack. So there's no need to remember the operand stack in this dump anymore. The same we can do for control. So we can actually come up with a global control. So that means when a function gets applied, we simply put the body of the function on top of the existing control with the addition of an instruction that returns from the function. What does that return do? The return instruction will simply re-establish the previous environment. So the only purpose of this dump is now to store the environment. Previously, we needed the dump to store the operand stack, the environment, and the control. Now we only need it for the environment anymore. Well, if we only need it for the environment, we might as well put that environment in the control. So that's the last step. So in this version, we don't have any dump anymore, and we put the environment directly in the control as an environment restoration instruction. So instead of a return instruction, we say, okay, when you get here, just use that environment in the future. That's what's happening here. So if during the execution you find such an environment restoration instruction, you simply replace your current environment with that environment. That allows a very simple mechanism for execution. All right, so I'm going to skip all of this. You can play with the Source Academy. Let me just very quickly flash how you could run this program. So this is a factorial program, and if you run this program in what we call the CSE machine here, you get a visualization of the running program. So here, this is how we teach our students to understand what happens when programs run. So you can actually see the execution of the program like this, step by step, and this directly corresponds to this CSE. So you have the control here on the left, you have the stash on top, and you have the environment here. So I'll visualize this nicely. Our CS 111 students will have fond memories of the CSE machine from taking their course. Yeah, so that's basically how we translate this mechanism into visualizations, animations for students to understand what happens when programs run. So, so that's just to give you a bit of a glimpse at what happens. Yeah. So at the moment, I'm working with a bunch of students to extend this framework to other languages. So we have 4 ongoing final year projects where we basically come up with an environment in which we can run Python programs in the same way as you have seen it just now, JavaScript programs. Scheme that includes a special construct called call.cc, continuations, first-class continuations in the language can also be very elegantly expressed in this framework. And Kirill, the person in charge of our language implementations in the Source Academy, and we have a paper on this at the Scheme conference last year. And we have an approach to visualize C programs also in such a framework without reference to a compiler. So we want to explain realistically what happens when C programs run with a proper memory management, with a proper idea of what happens inside the memory, without saying, oh, there's this compiler that generates this code. No, we want to have a realistic mental model without reference to a compiler. Java, the same. We had 4 final year project students to visualize the execution of Java programs basically along the same lines. Go is an ongoing final year project, going in the same vein. And that's basically where we are in this effort to come up with frameworks that allow students, first semester students, to understand what happens when programs run. Thank you.